In the last units of this short Mathematics for Deep Learning course, we'll touch upon information theory. The very basics of information theory. In particular, we'll introduce concepts such as the self-information, Shannon's entropy, or the Kullback-Leibler divergence. Information theory is a branch of applied mathematics, and its goal is to quantify how much information is there in a given signal. And really the father of information theory is Claude Shannon, who in 1948 published the seminal work, A Mathematical Theory of Communication. And in fact, 1 year later, this work appeared as a book with a small change in the title. It was called The Mathematical Theory of Communication, which indicates that already by that time it was widely recognized how important that paper is, and it was the founding work for an entire field. It spawned the entire field of information theory. So here is it. This is a screenshot of the original 1948 paper offered by Claude Shannon, A Mathematical Theory of Communication. And let's just have a look at the first few lines of this work, where he writes, "The recent development of various methods of modulation such as PCM and PPM, which exchange bandwidth for signal-to-noise ratio, has intensified the interest in a general theory of communication. A basis for such a theory is contained in the important papers of Nyquist and Hartley on the subject. In the present paper, we will extend the theory to include a number of new factors, in particular the effect of noise in the channel and the savings possible due to the statistical structure of the original message and due to the nature of the final destination of the information." That's something we'll touch upon now. The fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. Frequently the messages have meaning, that is, they refer to or are correlated according to some system with certain physical or conceptual entities. The semantic aspects of communications are irrelevant to the engineering problem. The significant aspect is that the actual message is one selected from a set of possible messages. The system must be designed to operate for each possible selection, not just the one which will actually be chosen, since this is unknown at the time of design. So here's a little anecdote about Claude Shannon that I found in the Bishop book. So Claude Shannon lived 1960 to 2001. And after he graduated from Michigan and MIT, he joined AT&T Bell Telephone Laboratories in 1941, where he also wrote his famous paper, A Mathematical Theory of Communication, published in the Bell System Technical Journal in 1948. And this paper laid the foundations for modern information theory. The paper introduced the word bit, and his concept that information could be sent as a stream of ones and zeros paved the way for communications revolution. It is said that von Neumann recommended to Shannon that he use the term entropy not only because of its similarity to the quantity used in physics, but also because nobody knows what entropy really is. So, in any discussion, you will always have an advantage. So we'll hear about entropy in a few minutes here in this short course. This is a picture from Shannon's work. We can see the structure of the system that he considered, which is there's an information source that produces a message that's then transmitted via a digital signal and received at the receiver side and then decoded again at the destination into its original form. And this channel here is subject to potential noise. So that's not something we will consider today, but that's what information theory is about. So information theory, to recap, was originally invented to study sending messages from discrete alphabets over noisy channels. For example, communication of messages via radio waves. Information theory tells how to design optimal codes for those messages and how to calculate the expected length of messages sampled using various coding schemes. And we'll see a very simple example. Here we mostly use, here meaning in this short course, we mostly use a few key ideas from information theory. The field is huge, and we can't even cover this original paper. Not even a tiny bit. So we'll just use a few key ideas from information theory, and we'll use them with the purpose of characterizing probability distributions, or quantify similarity between probability distributions. That's where information theory comes into machine learning in the context of our courses. Okay, so let's now dive into the notion of information. What is information? The basic intuition is the following. The basic intuition behind information theory is that observing an unlikely event is more informative than observing a likely event. Let me repeat. The basic intuition behind information theory is that observing an unlikely event is more informative than observing a likely event. Okay? Intuitively that makes sense, right? Let's see an example. The message, "The sun rose this morning," is completely uninformative. The sun rises every morning. It's not worth sending this message. It doesn't contain any valuable information because the sun rises every morning. Every single morning the sun rises. There's no information if you tell me this. In contrast, the message, "There was a solar eclipse this morning," is very informative. It's actually rather rare that a solar eclipse happens. And so if you tell me there was a solar eclipse, then this is quite informative to me. This is the basic intuition. Unlikely events such as the solar eclipse contain more information than very, very likely or extremely likely events such as the sun rises every morning. In contrast, the solar eclipse is a rare event. In other words, receiving this message surprises us. Surprise is another word for information. We'll quantify information content informally as the level of surprise, if you will. If we're surprised, this means we have gained information that was before not known to us. We would like to quantify information now in a way that formalizes this intuition. Likely events should have low information content. Right? Sun rises every morning should have low information. And certain events should have no information content. Actually, the sun rises every morning is certain. So it should have zero information. However, less likely events should have higher information content. And the third rule that we impose is the following, that independent events, if you observe independent events, then the information should add up. They should have additive information. As an example, finding out that a tossed coin has come up as heads twice should convey twice as much information as finding out that it has come up as heads once. If I toss a coin, it comes up as heads twice. This should contain twice as much information. Now, given those assumptions, there's only one formula that can fulfill all of those. To satisfy all of those requirements, we define the self-information. We call this information quantity the self-information of an event x equals x. So here we have a random variable x taking a value x as I of x equals minus the logarithm of p of x. where in this case the logarithm refers to the natural logarithm with units of nuts. This is the terminology for the unit, nuts, if we use the natural logarithm. And the self-information is always bigger or equal than 0, just through the definition of this formula, through the properties of the logarithm. Note that if we use a different logarithm, this is equally possible, but then the unit changes. So for example, if you use the logarithm to basis 2, then this is called bits. And it's just a scaling. So we can, because we just need to multiply or divide with the respective logarithm, we are just effectively scaling. So there's just a scaling factor in between nuts and bits, or information expressed in terms of the logarithm to the basis 10. Yes. So it is possible to show this, that this is the only formula that fulfills these requirements. But it's also quite easy to see that, because we know that via the rules of the logarithm, that if we have a logarithm of a product, then this is the sum of the logarithm. So we have this additive requirement here fulfilled. We also know that minus logarithm of something is always positive, and the smallest value it can take is 0. And we know that if the probability is higher, then the information will be lower, because this is a monotonic function and we take the negative of it. So these two conditions are also fulfilled. Self-information is minus the negative logarithm of the probability of x. Okay, so here we have the definition again. To satisfy all requirements, we define the self-information as such. Self-information of the event that x takes x. A few remarks on this. Self-information is also interpreted as quantifying the level of surprise, as we've already learned. And one nut is the amount of information gained by observing an event of probability 1 over e. When using base 2 logarithms, units are called bits or Shannons instead. And information measured in bits is just a rescaling of information measured in nuts. Just need to rescale. Let's look at another example, a simple example on this additiveness. So let's consider a fair coin toss at first. Let's consider a single fair coin toss. So we have this coin and can either turn heads or tail, show up heads or tail. So if we throw it once, then the probability, if it's a fair coin, of coming up heads is 1/2. So if we are now considered in the logarithm to basis 2, then the self-information is minus log 2 1/2, which is equal to 1 bit. If we now consider this situation here where we have 2 fair coin tosses, and the event of each of those happening is 1/4, then the information of observing this is 2 bits, minus log 2 of 1/4. You can see that we have this additive effect here. 1 bit plus 1 bit is 2 bits by observing these two independent events. On contrary, let's go back to a single coin toss. If we have an unfair coin that always comes up heads, I'm not sure if that's physically possible, but assume there's a coin that comes up always with heads. So it's a very unfair coin. The probability of this happening is 1 now. And so the information for this event is minus log 2 1 is 0 bits. Because it always comes up with certainty, comes up with heads, we have 0 bits of information as desired. Let's now move on to entropy, so-called Shannon entropy. Self-information, as we've seen it, deals only with a single outcome. But we can also quantify the amount of uncertainty in an entire probability distribution. And we do this using the so-called Shannon entropy. We write Shannon entropy as h of some probability distribution p of x. And it is defined as the expected self-information when x is sampled from that distribution. And so that can then be rewritten by the definition of the self-information from before as minus the expected value of the logarithm of p of x. In other words, the entropy h of p is equal to the expected amount of information when drawing from p of x. As the self-information is positive, the entropy is also positive, right? The expectation doesn't change anything. We're just summing up and weighting by the positive probabilities. So if I is positive, then E of I must also be positive. When using base 2 logarithm, the entropy specifies a lower bound on the number of bits required on average to encode symbols drawn from a probability distribution p of x. When x is continuous, the Shannon entropy is known as differential entropy. So many of these concepts that we see here not only work for the discrete case, but also for the continuous case. And in this case, we call this Shannon entropy the differential entropy. And so here's what it looks like. In the first case, we have the discrete setting where we have specified the Shannon entropy here on the left. And then because we are in the discrete setting, this translates into minus the sum over all possible states p of x times logarithm of p of x. This is just the definition of the expectation. And then similarly for the continuous case here at the bottom, where the summation is simply replaced by an integral. As a quick remark, by convention we treat 0 log 0, which can occur here, as the limit of x log x for x to 0, which is equal to 0. So 0 log 0 is considered to be 0 if this occurs in any of your calculations. Let's look at some examples. The simplest example is to look at the Shannon entropy of a binary random variable. Think of a coin that is either fair or unfair. So what we have here in this figure is on the bottom we have the probability p of a binary random variable, like a coin, being equal to 1. So for a fair coin we would have 0.5, but for an unfair coin we would have maybe 1 or 0. And on the y-axis we have the entropy of the corresponding Bernoulli distribution, which is h of p equals, now we have just these two states because it's a binary random variable. So we have like two terms now, right? So we're doing this expectation, but we have just two states. So the first one is minus 1 minus p log 1 minus p, or the other side of the coin turns up minus p log p with the probability 1 minus the other one, right? So this is the entropy, this is showing the entropy, and this is actually the curve that shows up if we plot this expression here. What we observe is that indeed, if we have maximal uncertainty, if the distribution is close to uniform, 0.5, if p equals 0.5, the entropy is high, takes the highest value, just below 0.7, if you do the calculation. But on the other hand, if the distributions are close to deterministic, meaning that the coin always turns up head or tail, then in this case the Shannon entropy will be close to 0. Right? So if we have a completely random distribution, uniform distribution, then we have high entropy. If we have events that take place with high certainty, then we have low entropy. So this is a simple plot that we can do because we are just considering a binary random variable. But we can also look at other distributions. In this case, we have histograms of discrete probability distributions over 30 bins. Right? So this is a discrete distribution over 30 different bins. And we show also the entropy in nuts here at the top. And what we can see is that the entropy of the broader distribution, as expected, because it's more uncertain, is higher than the entropy of the more narrow distribution, where it's more clear which states will be taken when sampling from that distribution. And again, also in this case, a uniform distribution would yield the largest entropy possible. So if we would have a completely uniform distribution here, then the entropy would be, well, we would have, if we go back to the formula, we would have 30 times 1 over 30, because every, this p of x, every of these is equally likely now, and this cancels, so we don't see it here. And we are left with minus log p of x, which is minus log 1 over 30. And so this is equal to 3.4 nuts, which is the highest possible entropy that we can have for this particular distribution. Now, to conclude this unit, I want to briefly show you the relation to the shortest coding length that was so important to Shannon when transmitting messages from the sender to the receiver, and how this relates to the entropy. So it's not only useful as a measure of probability distributions or uncertainty for us, but it also relates, it's founded in this coding. So what is this about? Consider a random variable x with 8 possible states, a, b, c, d, e, f, g, h, and a distribution on that random variable x, which we call p of x. If each state is equally likely, the entropy is, well, h of p is minus 8 times 1 over 8, because there's a uniform distribution, log 2, now we're operating again in bits, we're taking the logarithm to the basis 2, 1 over 8. And this is, if you do the calculation, 3 bits. Okay, this is the entropy of the uniform distribution over 8 possible states. Now let's assume a non-uniform distribution. In particular, let the probabilities be, as we see them here. The first state is extremely likely, has half of the probability mass, or half of the probability. And then the second half of the probability is split across all the other states, where the second state is still quite likely and the third state as well, but then the remaining states are rather unlikely. In this case, we can also compute the entropy. So we have minus 1/2 log 1/2, minus 1/4 log 1/4, and so forth, until minus 1 over 64 log 1 over 64. And this is 2 bits if you do the calculation. So we can already see that also in this case, if we have uniform distribution, the entropy is higher than if we have a non-uniform distribution. Okay, so what does that have to do with the shortest coding length? Well, the non-uniform distribution has a smaller entropy than the uniform one, but what has this to do with the shortest coding length? Let's consider coding a message to be sent from a sender to a receiver now. What can we do? Well, we can, because we have 8 possible states, we can simply naively encode this message by encoding each single symbol in that message using a 3-bit number, right? With 3 bits, I can uniquely encode messages with 8 characters, alphabets with 8 characters. However, in the case that the probability for these characters looks like this would be quite suboptimal. And this is what the difference in entropy between these two tells us. Because what we can do instead is we can use shorter codes for the more probable events at the expense of using longer codes for the very unlikely events. So for example, we can take the code 0 for the symbol A, and the code 10 for the symbol B. As you can see, they are quite short. And then these symbols E, F, G, H, which have low probability, we encode with longer codes, like 111100. And if we do so, and if we assume that this, or if we generate messages from that distribution here, then what we'll observe is that the average code length now equals the entropy in this case. Right? Because with probability 1/2, we have a code length of 1. We're encoding symbols with a code of length 1. With probability 1/4, we are encoding the symbol with code length 2. And only with probability 1/64, we need 6 bits to encode a symbol. And so on average, if we do the calculation, we obtain, again, 2 bits, like the 2 bits that we have come up with here, which is the entropy of this distribution. So the entropy tells us something about how many bits we need if we, in an optimal way, encode these messages. As a little remark here, note that shorter codes cannot be used while uniquely disambiguating symbols. Right? We need to know when a symbol ends, so we can't use any arbitrary code here, but we have to encode these symbols in a clever way such that we can make a distinction. For example, this code here, 11001110, uniquely decodes into the sequence CAD, right? Because 110 is only a code where a single symbol starts with, which is a symbol C, and then 0. This is the code where symbol A starts with. And so this is all unique. That's why these codes look like that.